So in our last video, we started talking about how to approach these rigid body planar kinetics problems, right? So this is when we have some kind of motion of a rigid body, and now we're dealing with forces. So in our last video, we introduced the concept and we said, this is how you do it for translation. So we're also going to, in this video and the next video, talk about rotation about a fixed axis, as we did with our kinematics, and then move into our general plane motion. So for our planar kinetics, when we have rotation about a fixed axis, so again, that's if we have something that is just rotating about a fixed axis, something like a flywheel or something moving around a pin, but the body isn't translating at all, it's just rotating about this fixed axis. It's best for us to use the normal and tangential components for our equations of motion when we're dealing with this. So our equations of motion are still going to be our sum of forces equals ma, and our sum of moments is now going to be a factor, right? So our sum of moments was 0 when we were looking at translation, but now we're going to have our sum of moments equal our moment of inertia times the angular acceleration, since we're going to have an angular acceleration in these rotation problems. So our equations of equations of motion that we're going to be looking at here, since we're moving in these rotations, it's going to be easiest for us usually to work with the normal and tangential components. So some of our normal forces is m times ag in the normal direction. And for our purposes, most of the time, it's really going to be easier to write this instead of m times ag in the normal direction, to write this as mass and then substitute in for agn omega squared times rg. So that's your mass times your angular velocity squared times that r, which is the distance to the center of mass. Distance from your rotation to your center of mass. And then we can do the same with our sum of forces in the tangential direction. Instead of writing mass times acceleration in the tangential direction, we can write it as mass times alpha, which is the angular acceleration, times rg, a distance to the center of mass. And now the one thing that's going to be different for our planar kinetics when we're doing rotation about a fixed axis, and I guess I should say about a fixed axis up here. Rotation about a fixed axis. We're going to have actually 3 different moment equations we could use for any given problem. So when we were looking at translation, we said there was no rotation happening, so our sum of moments about g was just 0 for translation. For rotation, now we do have that alpha, we have that angular acceleration, so our sum of moments about the center of mass equals our moment of inertia about the center of mass, so that's ig, our moment of inertia about the center of mass, times alpha. And alpha is that angular acceleration that we've seen, that we've worked with before. So this is one of the possible moment equations we could use. Or we could use the sum of moments about point O. So point O in this case is going to be like the point that you're rotating about. Sum of moments about point O is the moment of inertia about point O times the angular acceleration. So that's another one that we could use. Or we could also use the same equation that we had used in our translation, which was sum of moments about any point is the sum of the moments in the kinetic diagram about a given point. So any of these 3, we'll only use one of them for any given equation. We can pick which moment equation we want to use in combination with these 2 force equations up here to solve for any forces, acceleration, or whatever the problem may be asking for in these planar kinetic problems, right? So typically forces and accelerations are what we're working with in these problems. So what we're going to do is a lot like translation. We're going to establish that normal and tangential coordinate system, draw the free body diagram and kinetic diagram, and then really the only new thing is adding in needing to solve for IG or for IO. Either of those, we need to find that moment of inertia, and then we can apply these kinetics equations to solve for our forces or accelerations or whatever our problem is needing us to solve for. So we'll take a look at a couple of examples to make a little bit more sense, but it's going to be pretty similar to our translation. Just know you have more moment options and that we're pretty much always going to be working in this normal and tangential coordinate system for these problems. So let's look at our first example here. We've got a 20 kilogram slender rod that has an angular velocity of omega equals 5 radians per second. Determine the angular acceleration of the horizontal and vertical components of the reaction of the pin on the rod at this instant. So what they've given us on the left here, we can see it's pinned at O on the left side. There also seems to be an applied moment of 60 newtons per meter, and we have that angular velocity of 5 radians per second at that moment. So we're trying to find our angular acceleration, and then the horizontal and vertical components of the reaction at the pin. So let's draw ourselves a free body diagram. That's usually a pretty good way to start these. So I'm going to draw just my free body diagram here with all of my forces on it. So of course it's pinned there at O, so it's going to have those reactions of the pin at O. And actually maybe before I do that, it might be a good idea to establish this coordinate system. So we know we've got this thing that's rotating about a fixed axis. So that tells us we probably want to use our normal and tangential components. And then we can see that it's swinging downwards. It's going to swing down and to the left as it moves around point O. So when I set this up, I'm going to have my normal component go along the rod and the tangential component comes off of the rod, right? So if I did it like this, this would be my my tangential direction. And then my normal direction we usually have is going like up the rod. If I look at the end there. So I'm going to say this is my N, this is my T. And you could do it either way. You know, if it makes more sense to you, you can do N and T. I'm going to keep my T in the negative direction though, just because that is the way that our bar is swinging. So that would make a little bit more sense to do it that way. And maybe I'll use this one instead. Again, you can set it up in a way that makes sense to you, but I'm going to go ahead and use this, right and down system for my normal and tangential. And what I'm going to have here is my normal and tangential components of this pin reaction, right? So I have O in the normal direction and O in the tangential direction. So I've got those. I've also got that applied moment of 60 Newton meters acting, it looks like it's acting at point O. And this rod has a weight, right? It tells us it has a mass of 20 kilograms. And so it's going to be acting at the center of mass for this slender rod. And that's going to be that the weight is 20 kilograms times 9.81 to turn that into a force. And those are all of the forces that I see, right? So I want to capture all moments and all forces in my free body diagram. And I think we've captured all of them here now. So next we'll do a kinetic diagram. and kind of look at how this thing is moving. Right, so obviously we have that this thing is going through this angular velocity of 5 radians per second. But we also need to account for how the shape is moving, right? So we have, with respect to the center of mass, the bar rotates in the tangential direction 20 times AGT, and in the normal direction there is also an acceleration, otherwise it wouldn't swing, of our mass times AGN. Right, so both of those are being accounted for in our kinetic diagram here. Now there's also one thing that we didn't talk about in our translation that appears on this kinetic diagram, and it's that there is the moment. Our moment of IG times alpha. So IG being the moment of inertia about the center of mass. So this is acting about the center of mass right here, times alpha. It's undergoing that angular acceleration, and this gives us a moment that's acting about point G. So not only now do we have the two forces, but there's also a moment in our kinetic diagram. And there will be anytime we have these rotations that are happening. The rotation or general plane motion, this IG alpha has to appear in our kinetic diagrams. So now that we have that, we can find what that IG is for this shape. So it can also be a good idea to help when you set these up, find out what that IG is. And if we look at this, we have a 20 kilogram slender rod. And that IG about the center of mass there, we can go look up in our table, and I see thin rod about the center here is 1/12 ml squared. 1/12 ml squared. So IG is 1/12 ml squared, or 1/12 times 20 times, it has a length of 3 meters squared, and that gives me, I think it gives me 15. A moment of inertia of 15, and then if we plug it back in here, we would end up with 15 alpha for that moment. So our IG is 15, and then this we could plug in and say this is 15 alpha. So really important to make sure we capture that moment aspect in our rotational motion. Now that we have all of the setup done, we can move into those equations of motion. So I'll bring this down, and we're looking for alpha and OT and ON, those components of the pin. Alright, so my equations of motion, we had sum of forces in the normal direction equals, again, you can write MAGN, or you can have M omega squared RG. And if I plug in for that, I get, from my free body diagram, I get the left side. So from my free body diagram, I only have one force in the normal direction, so ON equals, and then from my kinetic diagram, I only have one item in the normal direction, and that's going to be in the negative normal direction, it looks like. 20 times, and then I've kind of removed direction from this by having this omega squared. So omega squared, 5 squared, times RG. And again, RG is that distance from O to G, from where we're rotating about to G. So here It's half of 3, which is 1.5. So that makes it pretty easy for us. We can find immediately what that ON value is. So ON is going to be 750 newtons. So that's one component of our pin. Let's do another equation of motion. Actually, I'm going to keep writing this in white. Whoops. Sum of forces in the tangential direction is mass times the tangential acceleration, which we know is m alpha rg. So for our forces for that left side of the equation, we're going to look at our free body diagram, and we have the tangential component of the reaction force at O. We have the weight, so minus 20 times 9.81. And I can see I actually didn't follow my own sign convention. My sign convention says that T is positive downwards. So let me flip the signs on this and just keep my sign convention straight. And those are all of the forces I have on the free body diagram in the T direction. And then I'll move on to this other side, my kinetic diagram. We have M is 20 times alpha, we don't know, and then times RG, which again, that distance is still 1.5 meters away. So I have two unknowns in this equation, not a lot I can do with it. I will go ahead and rearrange it so I can get OT is 196.2 minus 30 alpha. That way I can plug it into an equation later and I can solve for my alpha value. But for now, I'm going to leave it like that. And then my last step is that I have to do a moment. But I have 3 different options for moment equations that I can use. So I'm actually going to show you all 3 options and how they look a little bit different from each other. Again, you can use any of the 3 equations for moment, but you can only use one of them. So like you can't use multiple of them and try to string them together into something. You can only use one of the moment equations, but you can pick whichever one you want, whichever one you feel more comfortable with, or whichever one makes most sense for the problem. Sometimes a problem will be a little easier if you pick one over another. Sometimes it's trial and error. Sometimes you just like one and you just use the one that you like, and that's okay. You know, it might be a little more work sometimes, but you will probably get an answer. Probably. In this case, we can. I know for sure. I've run it all 3 ways, and we're going to run it all 3 ways right now. So your first option for your moment equation, and let me kind of just put it down here. So for option 1, you could do sum of moments about G equals IG times alpha. So sum of moments about G equals IG times alpha. Now, the left half of that equation is still coming from your free body diagram. So for this first option, we're taking a moment about G. So about G right here, which means we don't need to account for W, but we do need to account for OT. And don't forget, there's an applied moment on here. This 60 Newton meters is going to come with us. Down there. So we're going to have OT times his distance away, which is 1.5. And then 60, and he's just 60, because he's just an applied moment. And I'm actually going to make the positive direction for these as clockwise. Just because all of our rotation is naturally moving clockwise, that's what way our moment is applied, that's what way the angular velocity is moving, our angular acceleration is moving, so I'm going to say clockwise is positive. Means when I take this moment about this point here, both the moment from OT and that 60 are going to be positive. Again, I have OT times 1.5 plus 60. That was just from my free body diagram. Now I'm going to do IG times alpha. IG times alpha. So we found IG already. Found IG is 15. And it's literally just this IG times alpha term that we put on the kinetic diagram. That's all it is. It's 15 alpha. Equals 15 alpha. So we saved ourselves a little bit of time by already calculating out what IG was. But if you didn't do that up top, you would figure out to do it here when you're doing this moment calculation. So from here, we have a relationship with OT and alpha, so we can then plug in our OT value down here and solve this for alpha. Right, so we can plug this in. We get, here I'll write this out, 196.2 minus 30 alpha times 1.5 plus 60 equals 15 alpha. And then from plugging that in, we can solve for alpha, and it gives us an angular acceleration of 5.905 radians per second squared. And then of course we can back plug into this equation up here to find that OT equals 19.05 newtons. So that's one way we can do it. We can use that mg equals ig times alpha. Not too bad, right? Not too terribly complicated. Again, it was just pulling moments off of the free body diagram and then using that ig times alpha. But wait, there's more. So for option 2, something else that we could do is we could use the sum of moments about point O equals the sum of moments of the kinetic diagram about point O. And it could be any point, but point O is really the only other point that kind of exists. So it makes most sense to take a moment about point O here. So it's the same process of pulling moments from your free body diagram on the left-hand side of the equation, pulling moments from the kinetic diagram about O, and then plugging those in. Right, so our option 2 is if I want to take a moment about O right here, it means I don't need ON, I don't need OT. I do need the 60. I do need the 60, and I also need W. Right now, W is causing a moment. So I'm going to end up with 60 plus the weight, which was 20 times 9.81 times its distance away from O was 1.5. So that's the left side. The left side from my free body diagram up here. And then what I'm going to do is take my moments about point O of my kinetic diagram. So now not only do I need to include this 15 alpha, but now I have to account for this tangential component of my acceleration. Right, so 15 alpha still comes with us. It still comes with us. It's acting like an applied moment in the kinetic diagram. So this equals 15 alpha plus the moment caused by 20 AGT. And as we said, AGT is just alpha times R. So what we get is 20 alpha times R, which is 1.5, and then don't forget to multiply it by the distance away. 1.5. Right, so both of those have to be in there. It's mass times alpha times R times distance away. And we can see this one works out really nicely because it only gives us alphas. So this is a really nice one in that I don't have to plug anything in. I can just solve for alpha here and get 5.095 radians per second squared from my calculator. And then I can still back plug this in to find OT and still get the same number, 19.05 newtons. But wait, there's more. There's still a third option we could do, which is taking our moment. Here's the third option for moments. Sum of moments about 0.0. So left side of the equation is still the same as option 2. But now, saying that equals IO alpha. So the moment of inertia about 0.0, not point G, about 0.0 times alpha. Again, left-hand side still stays the same. It's all the same free body diagram. This is all of the same information. 60 plus 20 times 9.81 times 1.5. That all stays the same. The difference is that IO value. So to get the moment of inertia right here, right, of this 0.0 at the end of the rod here, I'm not actually accounting for the stuff that's going on here. What I'm going to do is I'm going to say, oh, this is a slender rod. I know the moment of inertia about the end of a slender rod. That was given to me in my back of my book, in my charts here. So if I take the moment of inertia at the end of this thin rod, it's 1/3 ml squared. Let me zoom in a little bit so you can see that a little better. All right, so this end here is designated by 1/3 ml squared, right? Through the center, it's 1/12 ml squared, but through the end point, it's 1/3 ml squared. So from our chart, 1/3 times m, which was 20, times L, which the overall length of it is 3, squared, times alpha. And interestingly enough, when we solve this for alpha, we still get the same value. Alpha is 5.905 radians per second squared, which again can be plugged into there and give the exact same OT of 19.05 newtons. So any and all of these three options are acceptable. All of them go with the fact that we had already done those first two equations of motions with the forces. Right? We did Fn and Ft, and then we could choose any of these moment relationships that made sense to us for this problem. Again, they're all correct. You just have to pick one and move forward with it. So it's a really good way to check yourself to see if you're getting the right answers. You have these three different options you can use, three different moments you can use to solve a problem. Again, some problems, it'll make more sense to use one over another. But for a problem like this, it's really your choice. It's your call, what makes the most sense to you in solving these. Let's go ahead and take a look at one last example problem. All right, for our last example here, we have a drum that's shown that has a mass of 60 kilograms and a radius of gyration of 0.25 meters. So if you remember our radius of gyration, that relates back to our moment of inertia. That K value is given to calculate moment of inertia. And that equation again is I equals mk squared. And that's going to be about our fixed axis there. All right, so we've got a drum of 60 kilograms, a radius of gyration of K equals 0.25 meters. A cord of negligible mass is wrapped around the periphery of the drum and attached to the block having a mass of 20 kilograms. If the block is released, determine the drum's angular acceleration. So this is kind of an interesting one because you can think of this system in a couple of different ways. You can treat it all as like one system together, one rotating system, or you can think about it like a block that's moving and then also a drum that's rotating and relating those two systems together. So I would encourage you to try this one, any number of different ways that you might think of that might feel more natural to you, and I'm just going to walk through one potential way you could do this problem. But just know there are multiple ways to get to the right answer here. So first I'm going to start with drawing out what my coordinates are. And so I'm going to say, all right, when this block is released, he's going to start rotating this way. So I'm going to go ahead and make that my positive direction for my moments. Make a counterclockwise as positive. And then out from point O, I'm going to go ahead and say that my tangential direction is downwards, the direction that the block is moving. And then my normal direction, I'm going to say, is to the left. Just to give myself a coordinate system, a positive coordinate system to work off of here. And so I'm going to start with a free body diagram of what I've got going on here. So I'm going to treat this all as one single system together, where what we have is this drum that is connected to this weight. So this is all one single system. We have this weight is going to be the 20 kilogram block times 9.81. There are reactions at the pin there. Right? So at O, not only do we have an OT and an ON, but we also have the weight of the drum. I should label these weight A, and then I'll call this weight D for drum, and that's 60 times 9.81. Alright, so I have the pin reactions, weight of the drum, weight of the block. That's all I've got going on in my free body diagram here. I'll also go ahead and draw my kinetic diagram of what's going on, where I have my drum. I have the acceleration from the force of that block there being mass times acceleration, 20 times A. And then I also, about point O here, we have this moment, right? We have IO times alpha. Don't forget, in all of these rotation problems, you should have either an IG times alpha or an IO times alpha. So here, we're rotating about this fixed axis. I have this IO times alpha. This is the way that my angular acceleration is spinning around this drum. And so from here, I can set up my equations of motion. I guess before I do that, we could go ahead and solve what this IO is, what that moment of inertia about O is, because we have radius of gyration. We know moment of inertia about O is mk squared, so this is just going to be 60 times our k value, 0.25 squared. Right, it's just the value for that drum. The block gets its own acceleration value, so it's not included in this. And this gives us 3.75 kilogram meters squared for IO. Okay, and what are we finding? The angular acceleration. We're trying to find alpha. So let's take these and we'll go ahead and set up our equations of motion. So our sum of our Fn equals m omega squared rg. Our sum of forces in the tangential direction is m alpha rg. And then finally we have our choice between whether we want to use sum of moments about g equals ig alpha, sum of moments about O equals IO alpha, or sum of moments about O or some other point, but O makes sense here. O is MKO. So moments equal the sum of the moments of our kinetic diagram. I think I'm going to start with my moment first on this problem. mostly because when I look at these forces for my n and my t, I kind of go, oh, well, do I have an omega? Did they give me one? I don't have an omega to work with. I don't have an alpha to work with. I'm trying to find it. So I think I'm actually just going to start with a moment. Plus, it's a little bit more complicated, right? The moment can be harder to think about. So I'll start with the moment instead of starting with these forces this time. So you can pick any one of these moments to work with, right? Any one of these three equations. I think I'm going to go ahead and use this last one here just to get some more good practice in using it. And the fact that this first one doesn't really make sense. Out of all three of them, we would have to calculate where G is because we have the block and the drum. Like both of them have their own masses. They have their own centers of gravity. We would have to find where the center of mass is for the system. And that sounds like a lot of work and I don't want to do that. So I would probably use one of these two just out of simplicity. But I'm going to go ahead and use this one at the end here just because I want to. Just because I think it'll be easier. Again, you can use any of them. It's totally your call. But I'm going to use the moments about my free body diagram here, equaling the moments of my kinetic diagram. So again, I'm going about point O, about the center of each of these. And if I look at my free body diagram, I only have one force that's not on point O, and that's going to be my weight. So this radius again, this distance here was given as 0.4 meters, just for reference. So I said that my counterclockwise was positive, so I'm going to have the force of 20 times 9.81 times the distance from O of 0.4. And that's it. That's all that goes on the left-hand side of my equation. That's all I get from my free body diagram. From my kinematic diagram, right, I want to pull my all of my moments from this. So not only do I have my moment from IO times alpha, I also have one from 20 times A. From 20 times A. So my 20 times A, that's the force, times its distance from O here is 0.4. And then we also have that IOA, and we found what IO was, right? 3.75, so 3.75 times alpha. I'm gonna, whoops, those up there. I'm gonna move this down here so I can work with this a little bit more. I'm gonna multiply that out. 78.48 equals 20 times 0.4 times A. Now, it may take a little thinking back of what our relationship between A and alpha is, but we do have a relationship between acceleration and alpha for rotation about a fixed axis, right? Our A is just alpha times R. So we can substitute that in. So I have the 20 times the 0.4 and then times alpha R. So times alpha, and we know that the radius is 0.4. And then that 7.35 alpha, that just stays the same. So from here, I can solve for my alpha value, and I get that the angular acceleration of this, when I punch all that into my calculator, is 11.3 radians per second squared, and that all came out positive. So it is counterclockwise there. And that's it. I actually didn't need to use those force equations at all, right? These were not necessary because I strategically picked a moment equation where I wasn't going to need any of this information, right? I didn't need any back solving by picking a moment equation that just allowed me to have alphas in it. So sometimes those moment equations can be really strategically chosen to simplify your life, right? To make it so you do just a little bit less algebra all the time. But you would still get there if you used one of these other moment equations. That would be just fine. You could still get there. Maybe you needed to use one of these as well. You could figure it out, right? There are lots of different ingredients, lots of moving parts in all of these dynamics problems. So just draw out your diagrams, keep trying, plug those things in from those diagrams and see if you can figure it out. Again, I would really encourage you to try this one a different way and see if you can still get this same alpha value. Just to prove that this does work multiple ways. And again, you could split up this free body diagram in multiple ways. So with that, in our next video, we're going to go a little bit harder, a little bit further into this with our general plane motion.